Couple quick announcements. Next TA tutorial is tomorrow. Kansas Quiz 4 should be open now. Remember, it's due this coming Friday. As I mentioned, this next couple of weeks, you're going to have a quiz each week to kind of keep the material moving through. So do pay attention to those ones. It's time to start planning for midterm 2. As I mentioned last class, last Friday is our midterm 2 cutoff material. So as we did before, start thinking about Piazza-type questions. Please start posting those up into Piazza. We will design a question based on that part through. From the last one, we actually used the multi-step transformation as an aggregate of a bunch of questions submitted by you guys. So do please. It's a useful thing to do. But it's a study tool. It also helps sort of just line up on things that you guys are still working on and still trying to learn through. Last class, we talked about the acetoacetic acid ester synthesis. This is kind of the analogy to the malonic ester synthesis. And we introduced the last two reactions, the Michael addition, Robinson annulation. Really what we're doing there is it's the same thing as the aldol reactions, everything else we've done, except we're subbing the electrophile. Instead of just being a carbonyl, it's now an alpha beta unsaturated carbonyl. This is where we're doing what we call conjugate addition. So, review question. What do you get when you put all these things together? Okay. So, does everybody have kind of an idea of the kind of product that you're making here? What if I told you your product has 0 nitrogens in it? So who has a product that still contains a nitrogen? Okay, it doesn't contain nitrogen. What's going on? So let's work it through these different parts. We are taking sodium methoxide and methanol. That's our base, that's step 1. If you look at your two components, let's identify these as donor and acceptor. This is addition to a conjugate system. You have that alpha beta unsaturated system over here. So this guy in green, that's probably your acceptor, that's your electrophile, which makes this your nucleophile. If we're going to do an acid-base reaction, we have alpha protons here and out here. In pink, those are going to be far more acidic because doubly stabilized, right? They're in between two pi coordinating systems. So we've identified what the molecule is. This is going to be my nucleophile. We've identified what center we're going to do our deprotonation on. That's because those the base we make at that, or the conjugate base we make from that one is more stabilized. So I will make a nucleophile. The enolate will be something like this guy. Okay, that's my nucleophile. My electrophile is going to be my alpha beta unsaturated system. So I'm going to make a new bond. Well, I'll draw the mechanism down into here, and we're sort of punching up electron density as we sort of like shuttle it along that way. So after that addition, we're going to get a carbonyl back. We're getting our nitrile back. We've got our new bond, and we've got this middle carbon here is this one we're adding into here, and N double bond negative. That's where we set basically the electrons that we've put through here. Now that's going to combine back. It's going to bounce back. It's kind of like the enolate-like equivalent. So after it picks up a proton, we'll settle in as new bond between the two structures, and then here with our second CN across there. Agree? This is the conjugate addition portion. Basically, after here, we've made our nucleophile, we've added to the electrophile, we've done a conjugate addition, we've added this kind of 3-carbon fragment to it. This is probably where we are after step 1. Next step, we're taking acid, water, and heat. And most importantly, we're also adding time. So what else happens here? Nitrile hydrolysis, exactly. If we do this conditions, acid and heat, normally what we'd be doing, this is a malonic ester synthesis or something like that. Normally what we're trying to do is cut down the carboxylic acid to a carboxylic acid and then decarboxylate. We don't have carboxylic acids here. Instead, we have our nitriles. Under these conditions, both of these guys are susceptible. So intermediate might look something like carboxylic acid there and carboxylic acid over here over time. But we're still not done. What else can still happen? That's just the hydrolysis. Yeah. Decarboxylation. You still have a 1-3 relationship with your carbonyls over here. This carbonyl, that carboxylic acid, is perfectly primed for that 6-member transition state, so we can still lose CO2 in that fragment. So final compound is going to look something like that. So it's like a surrogate to the acetoacetate synthesis. And then this fragment gives us our distal carboxylic acid between the two. So we're pulling together a bunch of different components from a bunch of different reactions. This is where now what we're doing with a lot of the chemistry we're still going to be focusing on. These are remixing species and procedures we've done originally. Yes?
When we did the enolate collapsing down and then attacking the nitro reagent, we made a negative nitrogen, which is less stable than if we had attacked the ketones instead. So isn't it more thermodynamically favorable to attack the ketones?
So question is, I am attacking the alpha, beta, and saturate system. It makes a nitrogen minus instead of attacking the ketone, which makes oxygen minus, let's say. This isn't just your normal nitrogen minus. This is a long extended nitrogen minus. So that's one part. Resonance helps us out here a little bit more than the other. It's possible, like if you did that other addition to attack into that other ketone, that would be more like an aldol kind of reaction, right? So I think that you could potentially say, yes, that might couple, but partly what we're trying to do here is, if I have enough base, this becomes my enolate. It's an obligate enolate, kind of like a Canova-Nagel reaction. Remember, in a Canova-Nagel reaction, we take a molecule like this, and because it's so acidic, it spends most of its time as the enolate, which means it doesn't have that carbonyl left over to act as an electrophile. That's kind of what we're hoping to kind of do as well in this point. But good question. All right, one more. We'll do this one speed round. You put these two guys together, catalytic acid and a Dean Stark trap. What do you make? Go. Okay. And time. So quickly, what is a Dean-Stark trap? What again? It's a piece of laboratory equipment whose job is to help us remove water from a system. What we're doing is usually we're boiling something where water is being produced, water is condensing away from the reaction and being separately collected and removed. So it's a way of drying things without adding something like sodium sulfate to the system. So if I'm doing that, if I'm drying a system, what's your product here? What's the functional group you are making by doing this? A ketone, a secondary amine, and drying gives you enamines, yes. So the carbonyl from the cyclohexanone, wow, why is that all erasing? Bloop, bloop, bloop. Carbonyl from here, that carbon center is this guy here. We're going to have a new bond to my nitrogen, where we're going to have our secondary nitrogen attached over here, and double bond over there. Water comes from hydrogen, oxygen, hydrogen overall is kind of how you could sort of look at it. But you're dehydrating the alpha center, azurating the nitrogen. Remember, think of the mechanism. This is going through, and nitrogen is attacking into the carbonyl. Then you're making that acetal-looking thing. And then you're going to be extruding water to give you your iminium as an intermediate, losing that proton to give you back this neutral species. This is your enamine. So why are we talking about enamines? It is now time for the wonderful world of enamines. We've been talking about enolates up until now. And again, the permutations we've been walking through is what happens if I have an enolate as my nucleophile, and I'm changing things like I'm attacking an ester, I'm attacking an aldehyde, I'm attacking an alpha, beta, and saturating thing. We're looking at mainly up until now as we permute through different electrophiles. Now we're going to change the nucleophile into our enamines. This means that nucleophilic enamines can still do the four kind of category reactions we talked till now. Alkylations, aldol type reactions, acylations, and then the Michael addition. So it's the kind of the different permutations of our different electrophiles. So as a quick reminder, alpha, beta, and saturated systems like this, these guys are really good at less nucleophilic additions happen to favor over here. The hard nucleophiles, Grignards, attack on the 1,2 type position. Things that we're looking more like our the enolates, the doubly stabilized enolates, those are going to attack at the green center in our 1,4 one. What we're going to find is the enamines that we're adding right now, or enolates in general, will typically attack in this kind of 1,4. And that's why we use these doubly stabilized ones. Enolates on their own can sort of vary in terms of how strong or how weak they are in terms of the nucleophilicity. Focusing on things that have these Canova-Nagel-like ones really ensures we get this 1,4 type addition. So what we're emphasizing here is that enolates on their own, while they're nucleophilic, they have a general range of stability depending on what their structure is. And that's why focusing on something that has these two different stabilizing pi groups allows us to focus on that type of chemistry. Now the downside with that is you've automatically said that only a certain structure, only a certain type of carbonyl compound can be used. If you have to go into something like we did back over here, it means that I need to find a molecule where I can, by default, make this stabilized type nucleophile, which limits some type of the functionality we're going to have to deal with. It's sometimes hard to make molecules that have these doubly stabilized parts. Sometimes I just want a normal ketone or a normal aldehyde to behave as if it was a 1,4 addition or a doubly stabilized material. So what we do here is instead of relying on an enolate, we're now going to use the enamine, which gives you back this kind of reactive stability. It's another way for us to say, I want all the benefit and selectivity of a doubly stabilized enolate, except I don't want to have to form a doubly stabilized enolate where then I'm stripping out or doing the saponification, that hydrolysis, and the decarboxylation. It opens up the type of reactions I can do, but it still gives you back your selectivity. So, as a reminder, enamines look like this, right? This is where we have this double bond as an alpha, beta, and saturated system. The nitrogen is our sort of looks more like an enol type structure. We've got the sp3 representation, but remember, this is only one of two possible resonance structures. The lone pair on the nitrogen exists in the neutral form like this. One of the intermediates you generate, or how you make your enamine, is through the iminium form. That's where we've got our double bond down through nitrogen, so the lone pair being shared into that sp2 center. which means you can rewrite it. The other resonance isomer is this Zwitter-ionic sort of structure like this, where we're formally charging that alpha center with our negative charge. All we're showing you here is enamines on their own are nucleophilic, and they're nucleophilic in the same position that enolates are. They're nucleophilic at this alpha position because they carry a possible negative charge at that center. So we can use them, if we can form these enamines, we can use them in the same kinds of reactions we've been doing for our enolates. The advantage is, again, to make an enolate, if this was a simple non-activated molecule, to make the enolate, I'd have to use LDA, some super strong base. What you're going to find is this allows us to do all of the sort of reactivity part of an enolate, of any enolate, but we're using a much more gentle reaction condition. This allows us to sort of do something without having to touch something like LDA. So as a quick reminder, this is our spectrum. You remember, this is kind of Goldilocks. Enolates, super nucleophilic, great to add, also kind of hard to form, right? If we don't have any stabilization, the alpha protons are actually quite not very acidic. We have to go to a very strong base in order to deprotonate here to make my enolates. Enols, they're still nucleophilic in that alpha position. The downside is there's really no way to form them. Enols are just the tautomer of my normal ketone. There's nothing else I can do to sort of force the enol form unless I had something like resonance stabilization. It's not something that I can take my general ketone and say, well, I want to convert it to my enol form. A ketone is always going to be your most stable form of your enol, and it's just a tautomeric equilibrium that allows you to access the enol form. So enamines is kind of the best of both worlds. It is more nucleophilic than my enol, but it is more stable than your enolate. You're not making this anionic molecule. It's still neutral, but it's more nucleophilic than your normal enol would actually be. And you can actually, we have chemistry that allows us to form the enamine when we want to. It gives us control over it to say, I can take a ketone or an aldehyde, I can form my enamine when I want to, and then use it the same way I might use an enol. Yes? Sorry, say that again? No, remember, first of all, this is a resonance form. One and the other does not exclusively exist. They both exist at the same time. They're just Lewis dot representations of the same molecule. Just like we talk about when I take an enolate can either be represented as an O- sort of resonance form. That's the one we typically canonically draw. However, we use it as a C- nucleophile because that center, that C- would generally be considered to be more reactive. So we're using it as a alkylation or a coupling at the carbon center representing this kind of spirit of it. Remember, we're not saying that one or the other is, we're not converting between the two. These are both representations of the same molecule. We're just emphasizing that if I had an enamine, it will act as a nucleophile using the carbon center, that alpha center, which is just representing sort of the delta minus charge that's been built up over there. That's all I mean. Make sense? Okay, cool. So again, main reason, why are we using them? We have a way of taking your average run-of-the-mill ketone and turning it into something that is not as difficult to form as an enolate. We don't need LDA and low temperature. It's also more nucleophilic than your typical enol. So it sits right in between those two. It gives us a bit of control back. Now, because what we're doing typically is we're starting with a carbonyl compound. I'm going to make the enamine I want, so I'm creating my nucleophile. I use the enamine, and then I'm going to get rid of that sort of enamine character. This follows the same kind of strategy as you have seen with protecting group chemistry. We're going to do some activation step, carry out the chemistry we want, and then get rid of that part. So it allows us to go through these into sequential ways. So generally, when we're doing enamine chemistry, at least stoichiometric enamine chemistry, you're going to follow this same sort of sequence where you always have step one, take the ketone or aldehyde that you want, use a molecule, a secondary amine, and you're going to make your enamine. So it's always going to involve the secondary amine as a condensation reaction with the carbonyl of choice. Then you're going to use the enamine. Use as a nucleophile. We're using the reactivity properties of that molecule in order to form a product. And then finally, hydrolyze that product to get rid of it, re-exposing our ketone again, right? So this is the overall transformation looks very similar to taking a ketone, making an enolate, and then reacting it except we're going it by way of this other pathway. All right, so step one. This is something we've seen, we talked about at the beginning of class again today. The enamine formation involves usually weak acid catalyst, pretty mild conditions, except main part is you have to remove water from the procedure. You're doing a nucleophilic addition to your ketone or your aldehyde. That's going to give you this aminol intermediate. This is like an acetal or a ketal, where we have both the O and N function now at this sp3 center. And then in the presence of your weak acid, you're going to be protonating this via that SN1 kind of pathway, eliminating that water, and then giving you your enamine product from this one. So this is a procedure. What we are going to do is generate this, and generally what we would do is I would put those two components together under dehydrating conditions, and I would make up a solution of my enamine ready to go. You typically aren't isolating these ones because water is a bit of a problem. We can definitely run reactions where we control the water, removing it from the system, but if I then took that solution of my enamine and I rotovapped it, I re-expose it to atmosphere, to water, it will hydrolyze very easily. So this is not usually something we go and make it like a bucket of it, hold it in a vial. We make it when we need to use it, we hold it as a solution, and then we carry the chemistry through. So you're usually seeing something as like 1, 2, 3 as your steps that you're applying. Now, as far as your amines, remember the job of the amine here is only to act as an activator. So typically we use these two. Remember, to make an enamine, it has to be a secondary amine, so that's why both of these are just a secondary amine sort of working center. And typically, again, we don't want to have excess carbon here. We're just using this as a way temporarily to activate the ketone we want and then use it to do other chemistry. So we really are just focusing on something that's small and easily nucleophilic. We use these ring structures because, remember, the lone pair here, that has to actually attack your ketone. What do you think the advantage is of going in a molecule like this where we've got these rings formed? Why do you think we arrived to these guys as sort of our best ones? Yeah. Exactly. Like in the end, we need to use, the first step of these reactions is, I need to use that lone pair in the nitrogen to attack a ketone. So what I'm doing is, instead of I am a lone pair, imagine my head is a nitrogen. If my head is the nitrogen, lone pair is here, I need to attack a center. If I've got alkyl groups flailing around, what I've just done is I've taken them and I'm like, if you tie your hands behind your back, it's making it far more nucleophilic to do easy addition. You're helping the reaction out by making it planar and making it easy to add to other centers. It allows us to use it to many different sort of molecules. If it was something like a secondary amine, you've got steric interaction that's going to become a problem. That's step one. We're making the enamine, and we're going to choose a secondary amine, usually something like the pyrrolidine or the morpholine as our molecule, cyclic secondary amines. Next, we've made our enamine. Pick your electrophile. And we have 4 categories. If you remember back through, when we talked all the way through enolates, we did alkylation first. We've done aldol type additions. That's the second oxidation state of our carbonyls. Acylation, that's kind of like our additions to esters. That's the higher oxidation state, so we can add an acyl group to these centers. And then finally, conjugate additions. So these 4 electrophiles mirror what we've been talking about with our acetal enolate additions up until now. And again, you can choose any of these molecules very similar to what we've done before. Now, typically, we don't usually do additions of enamines into esters. If we're going to do this acylation route over here, we pretty much stick to acyl halides. That just reflects that what we discussed at the beginning about the relative nucleophilicity. Remember, enamines, they're less nucleophilic than enolates, but they're more nucleophilic than enols. They're nucleophilic enough to attack the most electrophilic acyl species, like these acid chlorides. Esters are not quite electrophilic enough usually to engage with. So usually if we're going to do this kind of carbonyl type addition to that center, we're going to stick specifically to these acyl halides. Michael addition and conjugate addition, very common. It lets us set up a larger skeleton. Last step is the hydrolysis. After we've done the addition, much like what we've seen before, remember the nucleophilic addition starts with the lone pair on the enamine. We're using that as our bond forming step. That's going to generate a product iminium, And usually this is where we've attached one of this group. So this is the product after I brought in my R prime group, for example. This is after, in step 3, that I've done my acylation or my alkylation reaction. R3 is what I put in. This is the product I have. And what I want to do is now bring back water. So under acidic conditions, I'm re-exposing my carbonyl and getting rid of my secondary amine. That's now, I'm done with it. I can depart with that part and get back to my carbonyl. So the overall transformation is I'm taking a carbonyl compound and I'm just adding something to that alpha center, much like I would have done with an enolate, except I'm going by the circuitous route where I'm actually making my enamine, do the addition, and then hydrolyze the enamine in between. So we're going to look at all 4 of those additions in a little bit of detail. So the first one, let's say I did my condensation, I made this enamine. The enamine I have here would have been formed from, that used to be the carbonyl center, so that this was an aldehyde that I started out with, right? The other group over here is a hydrogen. If I started with whatever aldehyde here, I made this enamine. That enamine is going to do an addition where lone pair comes down. This is going to attack by like an SN2 type process. So it's, again, the same pathway we've seen with enolate additions. You're bringing down the electrons from your heteroatom. In this case, it's the lone pair and the nitrogen. And then you're using that double bond as my pi nucleophile to displace something else. This is particularly good when we have strong electrophiles. And usually things like allyl, benzyl, and simple methyl halides are the most common ones that you're going to use. As they get longer, this reaction does get a little bit slower. So these are the most productive ones. Usually we're trying to find very electrophilic centers. And again, we're just reflecting the fact that while these are nucleophilic, they're not quite as powerful as our enolates. So they work pretty well for sort of these middle kind of points too. You're kind of restricted though, because you really have to stick to these kind of 3 categories as your major ones. After that addition, this is your product iminium. The product iminium needs to be hydrolyzed with water. And again, all we're doing there is we're doing water addition to that electrophilic iminium center. That's going to give us back an aminal, and the aminal under acidic conditions, because you're adding water to it, will eventually go through the same procedure to give you back your aldehyde center. So tracking that part through, that is your carbonyl center from your starting material here to here. And what you're doing is you're functionalizing this alpha center with whatever group you brought to the party. So you're doing this alpha functionalization. Now, we're not going to talk about stereochemistry. These reactions will give you, it's a pi nucleophile, so you're going to get both enantiomers from this point. There's no control over which face you alkylate. Next one, too, generally, the geometry of this part here, this is primarily controlled just by thermodynamics. You're going to end up with ones that are typically trans, where the 2 bulky groups stay away from each other. So this is generally the geometry of your enamine starting materials. Yeah? Oh, sorry, say that again? Good question. So yeah, after this addition, if you follow these arrows here, this makes the iminium. Now, technically, yeah, this reaction has a proton. You could imagine this exists as a product enamine. Might look like this. Like that. Right? So the product, the iminium that you make as a product could deprotonate to give you a product enamine. Same thing though, under these reaction conditions, this guy right here will protonate under that hydrolysis and give you the same product. So it's really the same captured material. No, both is fine. Yeah, absolutely. Okay. So that's our alkylation. If we change the electrophile to a pi electrophile, something like a aldehyde now. So in this case, what we're doing here is I make this aldehyde. That used to be the carbonyl from my aldehyde. I've made my enamine across this one. My nucleophilic center is still this alpha center, and I'm adding to this other carbonyl over here. So mapping out those centers, that's my starting material, carbonyl. Here's my nucleophilic center, and then the aldol-like center over here. We're making a bond between that green and that red. Once again, stereochemistry, we do not have control. You're adding a pi-pi sort of system, so you have all different permutations of enantiomers and diastereomers that are possible here. And then once again, we hydrolyze this reaction, re-exposing that carbonyl across here. Now this is also exposing one other really important thing. If you look at this structure, this enamine I started out with came from, I made that from just that aldehyde, right? If I took that aldehyde, I'm condensing it to make that center where that's the nucleophilic alpha center. Ooh. Green is the nucleophilic alpha center I'm trying to work on. That's my aldehyde center. That's mapping out that sort of pink and green center here. If you look at your product, that aldehyde is consistent. This is my nucleophilic center. Here is my electrophilic. This guy right here, that's a what? It's an acceptor. What kind of acceptor would I call it? This is an aldehyde. It's an acceptor, but it has a special name. Starts with an O. It's an obligate acceptor because it can't make enolates, right? It has no alpha centers. But this is one of those examples that if I started with a molecule like this, and if I tried to do the direct aldol reaction between these two, there's a possibility that that pink aldehyde bottom corner might just react with itself. This is why using a reaction like this, I'm doing effectively a cross aldol reaction. I'm taking my aldehyde, I'm forming it into a nucleophile. It's only acting as a nucleophile now, and then I'm bringing in an obligate acceptor to it. So it gives me back control. That's partly why we use this, just like we had with our enolate generation. Remember, we had order of addition we could potentially use, where we add either to the strong base or not. This is just another way to do this, where we're doing it by chemical programming. We're making it into only a nucleophile in this particular way, which allows us to get a cross product like this a little bit easier to control. So, acylation. This is where we're now going to a higher oxidation state of our electrophile. Instead of the aldehyde, we're going to the one oxidation state up. This is the oxidation state 3, where we have a leaving group attached to it. So think of this now as that sort of combination between aldol and acylation. We have a leaving group just like in acylation reactions. We still have our carbonyl present there, so it's still a pi-pi addition. Remember, acid chlorides, they are the top of the line in terms of our electrophilic sort of centers. Once again, we're going to start off with this center was the carbonyl of our choice. That is our nucleophilic center, and we're adding it to this electrophilic carbon. So programming that out, there's my carbonyl, there's my nucleophile, that's the electrophile. And we get to this 1,3 diketone product. So it's similar to what we would get from Claisen reactions, right? Where I could potentially start with a molecule like the nucleophile in the start attacking to a carbonyl. Now normally, remember, if this was a Claisen reaction, I would have to have done something over here where I'm guiding it to that center. I would need like a double stabilization on that starting material, so my starting material would have had to been some kind of like acetoacetate type structure to make sure that that green center was my nucleophile. Because what do I have over here? Do I have alpha protons? Right? The molecule I would be starting out with, this piece here, the fragment, would have come from this carbonyl. So mapping it out, that's my pink center. My green nucleophilic center is this one over here. And the blue center, that one over there. To get the nucleophile, to select for that green center, what kind of enolate am I basically doing here? That is which? Kinetic or thermodynamic? I heard half and half. And that is definitely before the midterm cutoff, so everybody confidently says kinetic, right? The less substituted center is what I would normally be going for. If this was enolate territory, how do I select for the kinetic enolate? I do what? Strong base, low temperature. I can do all of this at room temperature. So you're gaining the whole point where I can start with a molecule like this, and I can make the enolate, which is only forming at this kinetic side. It turns out these are still under thermodynamic control, but enolates generally will form to the less substituted side. You're forming, like we're basically breaking the rules when it looks like enolate or sort of the more substituted component. Basically what's happening here is in order to make this double bond, these enolates typically will select for the least substituted center, giving us access to what looks like the kinetic enolate. The reason why it works, these are not enolates, these are enamines. This gives us a different substitution pattern because under the equilibrium control here, in fact, these two centers, you can actually imagine that double bond very rapidly can sample between those two. You can imagine, even though we draw it like this, that double bond is very simple to sort of add a proton and then flip over to the other side. Add a proton, flip over to the other side. We can actually equilibrate between both of those two geometries relatively easily by adding or subtracting protons. So that equilibration is actually quite facile. What happens, though, is because, think of that double bond, is it's sampling between those two sides, which one of those two geometries, this green one right here versus that pink one right there, which of those two do you think is more nucleophilic? Which one can add to a group easier? Green or pink? Green is less sterically encumbered. This is giving us a way to say, even though thermodynamically this should be most stable, but because I can rapidly sample between the two, the green one is going to be more nucleophilic. The reaction happens at that center effectively. So this is giving us back the selectivity and control we would normally have to go to low temperature LDA, and we're doing it at a much more feasible reaction conditions. This is why we go through this. Yes?
Let's say we were doing an alkylation with that one. Would we almost get, with an unencumbered nucleophile, would we get partial addition to both sides?
No, same thing. Because remember, again, if you imagine that both nucleophiles could coexist, whatever center can more easily be grabbed by the electrophile, so let's say it's a methyl iodide. Methyl can still attack the least encumbered center, the guy I've circled in green, far easier than the other, so you'll get good selectivity for just that point, generally. There will be some mix, generally, but that gives you sort of other control. Okay, last one is the alpha-beta unsaturated system. This is where I got a material like this, I can do this addition to give me an alpha-beta unsaturated component. So once again, nucleophilic center, what used to be the carbonyl. This is my electrophilic center, and I'm now doing this conjugate addition, adding a larger carbon chain. This gives us this product. Now again, this has actually got a special name. It's usually called the Stork enamine reaction. What we're doing is we're stitching in this longer carbon chain to give us this extended fraction. Why this matters is it gives us this thing which has this very specific pattern. If you note, we have a carbonyl here with this 1,5 spacing. This is kind of the same thing we have for things like the Michael addition, the conjugate addition reactions that we showed you in the last pack too. So if you're trying to stitch this together, we've got this larger sort of extension. We get our product from this geometry. That's our red center. This is our carbonyl. This is our nucleophilic component here. So, general recap. The first step, the open, is always the same. We're going to start off with our ketone-like compound, aldehyde or ketone. We're going to make our enamine, and that's usually under dehydrating conditions. And typically, you're going to pick a secondary amine, and usually we'll pick those simple cyclic ones. Then we use the enamine. We use it to do either an alkylation reaction, aldol type reaction, acetylation with an acid chloride, or these Michael additions. Those give us our actual functionalization. And then finally, we hydrolyze the enamine. After the reaction is done, after we've done this addition, we only get our second product. Now, when do we use them? Like I said, generally, this allows us to attack or functionalize the less substituted side. This is a function of having this under partial equilibrium type conditions. It also means, especially when we start to target these 1,4 additions, they have the same reactivity pattern of these doubly stabilized enolates. The same thing as our malonate type additions too. It gives us back the ability to say, I really want to do a conjugate addition. And if I really want to do a conjugate addition, I want to make sure that I'm adding with an enamine to start off with. It just means I can use the enamine where I only have to use a monoketone to start off with. What I mean is, I can now start off with that and reliably do a conjugate addition to make a molecule like this without any other functionalization or any other change. If I took a molecule like this and made its enolate, there's a possibility that I'll get some amount of 1,2 addition between those two centers. A standard enolate, like a lithium enolate, is on the order. It's nucleophilic enough that addition directly on 1,2 is possible to give you almost like acting like a Grignard reaction. In a normal enolate, if I was doing enolates, normally what I would have to do is go in with a molecule like this. If I have that group appended on there, I will get my conjugate addition, the 1,4 type product. The problem is I have to first make this guy, I have to have that other double activation in place, and I still have to strip it out. I still have to heat it and do a decarboxylation in order to get the same product. So what we're doing here is we're using this as a way of simplifying our starting material component, making this activated intermediate and doing chemistry similar to what we would have done around this. So again, these are two different pathways that reach the same product. These are just about choices of different starting materials. So let's use it. This is your molecule, this is your product. How would you make it using an enamine strategy? So take a second, look at it, try to do the decomposition, locate which fragments become, or where you're starting from and where you'd actually sort of make this as a product. We've given you one of the two starting materials as well. Specifically, you're starting from cyclopentanone as your ketone. Okay. So cyclopentanone is our starting material. In here, that's this chunk right here, right? That's your cyclopentanone piece. Using sort of the color coding we did before, that's your carbonyl, which means we're borrowing that as my nucleophilic center. Again, I could use enolate chemistry for doing this. As we discussed, if I made just the enolate on this, what is my electrophile in this molecule? This fragment over here, that must be the bond I'm making. What kind of electrophile is this? Remember, we had our four. Alkylation, yes or no? Not alkylation. Is it an aldol type reaction? No, because remember, that would make an alpha beta, that would make a hydroxy ketone. It's not acylation, that would make your 1,3. This has that 1,5 carbonyl. If I was to disconnect across this bond, that's like making this, where my electrophilic center here is this one right here. So we're adding this one. Whoops, that's not right. There you go. Doop. Oh. There we go. So 1, 2, 3 corresponds to 1, 2, and 3. It's an alpha beta unsaturated addition, so this is like a conjugate addition, right? This is our storic enamine synthesis. So like I said, if you really wanted to make this, your choices would either be, I've got to extend this to something like acetoacetate, a doubly stabilized material, and go that route. If I don't want to do that, my other option is take this guy, and we're going to condense it with a secondary amine. And let's just use simple pyrrolidine. That pyrrolidine addition will give us our enamine. That's our step 1. Where we've isolated this enamine. Again, it's usually in solution. We then bring the two fragments together. That's going to give me my product, iminium. Draw this after my addition as my iminium product, where we've added this fragment on to that center. Again, mapping it out, that's my electrophilic center, nucleophilic center, and parent carbonyl, which means last step is your H3O plus in water, mild conditions. Just treating it with that point will allow us to free this up and get that fragment through here. So now we're doing these other sort of, again, we're borrowing reactivity by doing this sort of intermediate transformation. Super cool part about this is these reactions can work so well that you can actually make them into really easy catalytic reactions. In fact, this is one of the first reactions that were identified as what are called organocatalytic reactions. Does anybody recognize this part right here? That cycle, pyrrolidine, if that was an amino acid, what does that look like? You guys should recognize this one. It's the only amino acid that's acyclic. It's called what? Proline. Proline is your catalytic active site that allows these kinds of reactions to happen in the body. This is exactly where this all part comes from. Okay, I will see you guys on Wednesday. Okay, so for our follow-up questions today, first one we're asked to do is make 2 synthetic routes to generate the compound below via a Michael addition, which means conjugate addition. We're adding to an alpha-beta unsaturated system as our electrophile. So let's say if we divide it across there, that makes, let's say this is my nucleophilic center, this would be the electrophilic center over here. Notice if that's my electrophile and we have this other carbonyl over here, you can imagine that there was a double bond in that position at some point. So the disconnection I've just done could have come from, let's say, an enolate with this kind of general geometry, nucleophilic center right here, and then the electrophile being an alpha-beta unsaturated compound like this. Now, as we've mentioned before, this specific enolate, what we've generated here, while it has the right presentation, the problem is this is a strong nucleophile. We would form it as a lithium enolate, and there's a possibility this one would both do 1,2 and 1,4 addition. So if we wanted to control it and shut down the 1,2 addition, the real molecule that we should be using is going to be a stabilized enolate. So we would use a molecule like this. So now what this does is it lets us make a deprotonation at this center. It forms a doubly stabilized anion. That anion is now predisposed to attack in the 1,4 type pattern. And we have this whole group over here, which we could remove. This is the ethyl acetoacetate type structure, similar to the malonic ester synthesis we did before. So that would be one possibility. The second one, if I didn't want to go through the acetoacetate type route, I really want to use, let's say, a simple ketone as my nucleophile. Electrophile remains unchanged. What we can do is put them together to make the enamine. So if I have the enamine and I do a condensation reaction, let's say on that, now I would have a molecule like this. That is going to act as our conjugate addition nucleophile, favoring that 1,4 addition pathway. Okay, for this structure, we're trying to make this target compound from these 2 fragments here. Now remember, with the synthesis, the first thing we should try to do is identify which carbons correspond to which carbons from our starting material to the product, or the given materials to the targeted product. Now in this case, we've got this ring system here as a key clue, where I'm going to label that one as carbon 1. That looks a little bit like this, where this 6 atoms here. Now notice, if we number these off, 3, 4, 5, and carbon 6 would be equal to 2, 3, 4, 5, and carbon 6. So take a note of that. Carbon 6 in our starting material, what used to be a carbonyl, which corresponds here, where it is now a carbon-carbon double bond. That looks suspiciously like something like the Dieckmann condensation, right, where we're doing an aldol condensation to form a ring. That means that carbon 5 here, this one, is ending up making a new bond to some other fragment. And that's where the second piece comes in. If you notice, let's look at this center here. We'll call that in red 1, 2, 3, and 4. That might correspond to, remember, this would be my electrophilic center for like a conjugate addition. So if this was carbon 1, 2, 3, and 4, that nicely lines up with carbon 4 alpha to the carbonyl, carbon 3 being my carbonyl, which also matches over my product, and then addition at carbon number 1 with this alpha center here at the green carbon 5. So it looks like we're doing that sort of addition between the two. Now, if we tried directly, let's say, to take this molecule and do an enolate generation, we have two problems. We need the thermodynamic enolate, excuse me, the kinetic enolate in order to go to this least substituted carbon number 5, not this one over here. And second, the kinetic enolate, if we did there, would have a problem of adding both 1,2 and 1,4. So if you wanted to really control it, this is best done by our enamine pathway. So the first step we're going to do is generate something with, let's say, a Dean-Stark trap, and we're going to make the enamine we need with the right substitution pattern. As I mentioned in class, what we can kind of think of this as is the enamine is actually fluxional. You could have the double bond at either of these two centers. However, the least substituted center is more nucleophilic, less sterically encumbered, makes it easier to do our attack. So if we took this enamine and we now add it to our alpha beta unsaturated system, I'll draw it like this for convenience. Now we're going to do a nucleophilic addition like this, and that's going to give us our new product after, let's say, cleavage. So we'll do nucleophilic addition followed by, let's just draw that product first. So if we just did this where we're mixing these two pieces together, the enamine will add directly like this. We're going to have a product iminium as we normally would draw it. We have our new bond here, and then we've got the conjugate addition product like that. Okay. Now from this point, what we have to do is carry out effectively the second step of a Dieckmann condensation. So we would treat it with a base, let's say something like sodium methoxide in methanol. We're going to use heat at this one because what we're trying to do is promote an aldol reaction under these conditions. And more importantly, we could even potentially do this with a bit of water present. What we're trying to do is make sure that we hydrolyze that component. Now, as long as there is both acid-base and potentially the presence of a little bit of water or something like that, you can imagine that we will release this, or we could potentially work up the reaction, the first step, to get back our ketone. But if we had a molecule like this, sorry, let me just move this up here. We've got this sort of addition here, and the rest of the material seem like this. Now in this condition, if we number this off, matching sort of what we drew before, 1, 2, 3, carbon 4, and then let's say 5 and 6, like that, that's going to map over the ring that we're generating here. To use this same numbering scheme we did previously, actually, I can be a bit more explicit, and using these two, that's green 6 and 5, that way. That forms the numbering scheme I've sort of denoted out in this first numbering. So under these conditions, we now have this nucleophilic center out here. That's where we're going to generate this enolate. The enolate can do a ring closing and aldol condensation, which is going to generate that second double bond.